So what does the second derivative say about a function? Well, the second derivative concentrates on the shape of the graph, and it introduces another turning point. Not so much of a local max or local min, but there's actually other types of turning points when it comes to mathematical modeling. So if the graph of a function lies above all its tangent lines on an open interval I, then the shape of the graph is concave up on that open interval I. So why don't we begin with some kind of open interval? Uh, you could call it A to B, and then what would the tangent line looks like? Maybe the tangent lines look like this, right? And I need to draw the function the tangent line here, but there would be an open hole here because it's an open interval. And so you can see where I'm going here. There it is. And this is a shape of a graph because the tangent lines are below the function. This indicates the definition of concave up. So this is what we describe as concave up. Okay, the function is this shape, we call it concave up. Another version of concave up would be this. This will also be concave up. Now, what if the graph of a function lies below all of its tangent lines on an open interval I? Then the shape of the graph is concave down. This time my open interval is going to be a little different when I actually use an entire number line. So open intervals take on different forms. It doesn't have to be a finite number a and b. Here is an open interval from negative infinity to infinity. That's another form of an open interval. Now we need the function to lie below all of its tangent lines. So maybe there's a tangent line here, tangent line here, tangent line here, tangent line here. And then I need to draw the actual function. And notice this shape is introducing the definition of concave down. Okay, so this is what we call concave down. Another form of concave down would be this, right? This was the open interval. Definition. This definition is going to be very interesting. This introduces a new kind of turning point for a model. Okay, let's go over it. A point D, f of D on a graph y equals f of x is called an inflection point. If f is continuous at D and the curve changes from concave up to concave down, or from concave down to concave up. So why don't we draw a few examples of this? So maybe your function goes like this. So this is concave down, and then this is concave up. And then this right here would be your df of d for your function f of x. All right, so that's an example. We could have more of these, right? You could also do something like concave up, and then maybe switch to concave down. So this is a very important turning point in mathematical modeling. And these are called inflection points. All right, these are called inflection points. There's different ways of seeing these. Here's another one. You could have concave up and increasing. And then you can have concave down like this. Once again, it introduces a very specific type of turning point called an inflection point. So these are very crucial in mathematical modeling. Here's one more. Okay, so your 4 examples of inflection points. Concavity test. This is what's good about the second derivative. It basically tells you the shape. Okay, it's going to tell you the shape. All right. Once again, we'll talk about intervals I here. Primarily, these are usually open intervals. If for all x in that interval, the second derivative is greater than 0, then the function is concave up on I. If for all x in I, the second derivative is less than 0, then the function is concave down on I. Now, remember, there's only 2 different ways to have concave up. All right, so, the second derivative here, you either have it like that, or you might have it like this. And usually it's on an open interval. So when we think about this very, very carefully, if you really do have an open interval, you probably are thinking, holes at the end. However, if you have an open interval involving infinities, they might not be holes, they might actually be arrows. All right. Now, what if the second derivative changes sign around d? If the second derivative changes sign around d, that means before the crucial number d in an open interval, and the second derivative changes sign in an open interval after d, then d comma f of d is an inflection point. All right. You're probably wondering, how do we get this d? So let's make note of that. I'll give you a hint. How do we solve for this d? What we want to do is have solve this equation here. And you're solving for d. So you basically set the second derivative equal to 0, and then solve for d, and then see if there are any sign changes. Now, if you don't like to use the letter d, you could simply use x, which is very common as well. That way people don't get these mixed up with their critical numbers. And you could always rename it to d later on if it is indeed a inflection point. Once again, the tip or the hint to help you do that is choose your own appropriate test values, but this time you'll be testing the second derivative in an open interval before d and in an open interval after d. Here is the second derivative test. Suppose the second derivative is continuous on an open interval near c. If you have a critical number such that when you evaluate the first derivative at that critical number, it gets you 0, and the second derivative evaluated at c is greater than 0, then f has a local min at c. The easiest way to remember this is actually by drawing faces, believe it or not. And so if you drew, let's say, a face, let's give it a 2 eyes here. The first case, number 1, basically says, oh, here's your derivative evaluated at c. Then you gotta have a what? A local min, okay? I'm sorry, first derivative. The slope of the tangent line evaluated at C is actually equal to 0. So one of the key aspects of this is that the second derivative must be continuous. Okay, that's the only way this has a chance of being able to analyze and actually come up with a result, is that the second derivative must be continuous on an open interval near C. So before and after C. What about the second case, or number 2? How do you remember that the second derivative here can be useful? Once again, you draw a face. But this time you have concave down, and your face indicates that you have a local max. Okay, so these little pictures here can help you remember the second derivative test. However, there's a downfall in the second derivative test. Sometimes the second derivative evaluated at that critical number is 0. Then the test is inconclusive. Then you have to go back and just use the first derivative test. So the first derivative test is more powerful. It is actually a stronger test. But, depending on the scenario, some people like to use the second derivative test. And the second derivative test could be useful for creating formulas in the sciences. So that's why it is here. It is another tool, and sometimes it is a very beneficial tool.